imposing a local SU3 cross SU2 cross U1 symmetry. The fermion content, 3 copies, 3 generations, each made out of 5 representations, 3 quark representations, triplets of SU3, and 2 lepton representations, singlets of SU3, all left-handed fields in doublets of SU2, all right-handed fields in singlets of SU2. There is a single scalar multiplet, singlet of SU3, doublet of SU2, hypercharge plus half, whose vacuum expectation value should lead to spontaneous symmetry breaking of the imposed symmetry into SU3 cross U1 electromagnetism. From that, let's see, it will be quicker here. We derived the standard model Lagrangian, renormalizable Lagrangian, kinetic term for the gauge boson fields, for the scalar field, for 3 times 5 fermion fields, 3 types of Yukawa matrices with either U right or D right or E right, and the scalar potential. And from that, we started our investigation of the phenomenology of the model, and we got to this point. That's the standard model spectrum, the list of elementary particles, namely particles of well-defined masses and well-defined quantum numbers under the exact SU3 color cross U1 electromagnetism group, the massive vector bosons W plus, W minus, and Z, the massless photon, the massless gluon, the single real scalar field, the Higgs boson, 3 charged leptons, 3 massless neutrinos, 3 up-type quarks, and 3 down-type quarks. So that's where we stopped yesterday. And the next step, no next step. We stop here according to this. Yeah, it doesn't work.
Is it the last slide?
No, this is not the last slide. But no, but the laser did work, so.
I think it's the last slide. You can check.
That's the next. I don't stop at the spectrum. I would like to see the interactions, the accidental symmetries, the parameters, and some tests. And then I'll stop with this. So we are now to the interactions, and we are always mainly interested in the interactions among the fermions, also about the scalars. See, the vector bosons, we call them force mediators. Okay? Each of them is related to one kind of interactions. The W and the Z to the weak interaction, the gluon to the strong, and the photon to the electromagnetic interactions. The fermions, we call them matter particles, because all the structures in the universe, we here in the auditorium, ourselves, the galaxies, everything is made out of these fermions, like electrons, protons and neutrons, or if you want, up quarks and down quarks, so we call them matter particles. The Higgs boson is somewhere in between. I usually call it a force mediator, the mediator of the Yukawa interactions, but we are also interested in its interactions and what happens to it in our accelerators. But yeah, so it's a question of name. But usually we are interested in the interactions of the fermions. So where do the standard model interactions come from? From L phi, the part, the scalar potential, there are the Higgs boson self-interactions. These are terms made only of the scalar field, so that's where it is. From the Yukawa interactions, by definition, it's the Yukawa interactions, 2 fermions and the Higgs. And the rich part of the interactions come from the kinetic terms. When we include in them the covariant derivatives, then the vector bosons and the gauge bosons appear there. And what the kinetic terms of the standard model give us are the photon-mediated interactions, that's electromagnetic interactions, that's QED. It gives us the gluon-mediated interactions, these are the strong interactions, that's QCD. The Z-mediated neutral current weak interactions, and the W-mediated charge current weak interactions. So from L-kinetic, we'll get these four. Actually, we encountered already QED, we encountered already QCD. What we saw, it still applies here. And we saw the Z and the W interactions in the lepton sector. So the main novelty in what I will describe now has to do with the Z-mediated and W-mediated, particularly the W-mediated weak interactions in the quark sector, which we did not see so far. So since we saw QED, QCD, I just summarize it on one transparency. So on the first line, LAFF bar, it's the photon interactions with the fermions. So the coupling constant is always E, and it has a coefficient which is proportional to the charge of the fermions. So for the charged leptons, the charge is -1. For the up-type quarks, it's 2/3, and for the down-type quarks, it's -1/3. And we said already that it's vector-like, couples to Dirac fermions, so it's the same coupling to the left and the right part of this. It's parity, charge conjugation, CP or time reversal, same, conserving. It's diagonal, and it's universal. Namely, in each sector, it couples in the same way to the three different, say, charged leptons, or, thank you, the three different up-type quarks and the three different down-type quarks, always the same coupling in each sector. And I mentioned that this universality is because these are an exact gauge symmetries, and we want these couplings to compensate for the non-invariance of the kinetic terms, and the kinetic terms are universal, and so that dictates that also the photon couplings are universal. Much of this applies also to the strong interaction. So the gluon couples only to quarks because the leptons are singlets of SU3 color, and so they do not transform under SU3 transformation. They do not need for their kinetic terms to be compensated by the gluon transformation. And all the quarks are triplets of SU3 color, and therefore it's one and the same coupling to all of them, this G strong over 2, to the 6 different species of quarks. And QCD is again vector-like, it couples to the Dirac fermions, same coupling to left and right in here, parity, charge conjugation, time reversal, conserving, actually except for this term which I omitted, which was epsilon mu nu rho sigma g mu nu g rho sigma, which is parity and CP violating, but doesn't play a role in the perturbative physics that I'm concerned with here. Diagonal and universal, again, because it's a gauge bosons that corresponds to an exact gauge symmetry of nature. A little bit about the Higgs interactions. I'll come back to it, I think, 2 chapters from now, when I discuss beyond the standard model. So the Higgs has self-interactions, h cubed and h4. It interacts with the massive vector bosons, either a single Higgs and 2 of these, or Higgs squared and 2 of these. And it couples via U-kappa couplings to all the massive fermions. And I wrote it here in such a way as to emphasize that all the Higgs couplings can be parameterized or presented as depending on the mass of the particle to which it couples. So in particular, it doesn't couple to massless particles. So no coupling to neutrinos in its coupling to fermions, and no coupling to the photon and the gluon, but only to the massive vector bosons. That's because actually the source, all of these were massless if not for the spontaneous symmetry breaking. So the source of all of these masses is in the interaction of all of these massive particles with the Braut-Engler-Higgs field, or if you want, with the vacuum. And so all their masses come from interactions with the Higgs. And this idea is actually tested and more or less proven by the L07 experiment. The L07 experiment measured the couplings of these particles to the Higgs particle. Their masses come from their interactions with the Higgs field, and if the field related to the particle, this scalar that has 125 GeV mass, if the masses come from the integrations to the field that is related to the particle that has been discovered, then it dictates what their couplings to the particle should be. So the L07 measures their coupling to the particle, to the Higgs particle. Their masses measure their interaction with the background field, and the fact that they correspond means that indeed the source of their masses are the interaction with the field related to the particle that was discovered. I hope this argument goes through. If not, I'll repeat it at some point. So the main point is that the Higgs coupling are proportional either to the mass in case of fermions or to the mass squared in case of the vector bosons of the field to which, of the particle to which it couples. So that tells us that the Higgs decays will be dominated by the heaviest particle whose mass is less than half the mass of the Higgs. If its mass is higher, then the Higgs cannot decay to a pair of such on-shell particles. And so the Higgs cannot decay, for example, to top-antitop. The top by itself is already heavier than the Higgs, so it cannot decay to that. So here is the list of the leading decay modes as predicted by the standard model of the Higgs: bottom, anti-bottom, WW star. I will in a minute explain what WW star mean. The Higgs cannot decay really to W plus W minus because the mass of the W, 80 GeV, is more than half the mass of the Higgs. Half the mass of the Higgs is 62 GeV. Then pair of gluons, tau plus tau minus, ZZ star. Again, the Higgs cannot decay really to two on-shell real Z bosons because the mass of the Z boson is 91 GeV. Charm, anti-charm. And given their masses, we can predict the branching ratios. So the dominant is the bottom, 58%, WW star 21%, pair of gluons 9%, tau plus tau minus 6%, ZZ star and CC bar 3%. So the things that are most easy or straightforward to understand are the decays into pairs of fermions, in which case the branching ratios are proportional to the masses, plus there is a factor of 3 for the quarks because they are in a triplet, so it gives in the calculation exactly their multiplicity. So the fact that there are 3 colors of bottom and 3 colors of charm give this factor of 3. W star and ZZ star, so it cannot really decay to these two, so it stands for a 3-body, 3-level decay, where one W is on shell and the other just is a propagator that then decays to two fermions. So it's really W and a pair of fermions coming from the W, or a Z and a pair of fermions coming from the Z. Soon there will be a picture. The Higgs doesn't couple to two gluons in tree level because the gluon is massless, or if you want, because the Higgs is a singlet of SU3 color. Both of these lead to the same point. So there is no tree level coupling, and this decay comes from a one loop contribution, where the dominant contribution comes from a top loop. In a minute there will be a picture, and you don't see here in the list, but it also decays to two photons. Again, no tree level couplings because the photon is massless, or if you want, because the Higgs doesn't transform under U1 electromagnetism, it carries no charge. So for any of these reasons, there is no tree level coupling. So again, it's coming from a loop. Now there are two contributions dominant, one from a W loop, it takes from a top loop, and they have destructive interference, which make this even smaller than otherwise. So it's 2 per mil, and yet this was the discovery mode of the Higgs. So in spite of it being so small, the branching ratios, only one of every 500 times that the Higgs decays, it goes into a pair of photons. This was the mode through which it was discovered. And the reason is that this is the cleanest experimentally. The experimentalist could most easily find the signal of two photons with more events than expected at 125 GeV invariant mass. So this is how it was discovered. Accompanied very quickly by also signals at the ZZ star and WW star. The couplings to fermions, decays to fermions were discovered later. And at the moment, Atlas and CMS have established, so have evidence, more than 3 sigma signal for 7 modes of Higgs decays: BB bar, WW star, tau tau, ZZ star, gamma gamma, Z gamma, which is not in the list, it's also small branching ratio, and mu plus mu minus, which is also not on this list because it's, again, the branching ratio is very small, but again, the signature is clean. So among the big ones, the ones that you don't see, is gluon-gluon. This is decays into jets, and there is a huge background. There is no way this can be measured by the experiments, and you don't see CC bar. That's the next challenge of these experiments. They are using now all machinery that they can employ, machine learning, whatever, to try. It's very difficult to say that some jet of colored particles has in it charm, and this is charm and not bottom. This is difficult for the experiment, but they are on their way to that too. So what one can hope for in the future is particularly for CC bar to be added to this list. So here are the pictures. I hope I wrote it on my board in my home office, and I hope it can be seen here. So Yukawa couplings give Higgs to BB bar, tau plus, tau minus, CC bar. Higgs to Z star, there is one Z here, and the other Z is off shell and give us, for example, a pair of lepton anti-leptons. So the final state that is observed is essentially Z, L plus, L minus. Similarly, the WW star, one is a real W, and the other is just this propagator, which gives a pair of charged leptons and a neutrino. These are the ways in which this is observed. Here is Higgs to a pair of gluons, which was not observed. The Higgs goes to TT bar. They close a loop and emit gluons, and two photons is either a W loop or a top loop. So we'll come back to the measurements. I'll have one chapter on Higgs decays as explode and what they can tell us and how they test the standard model. It's a rich program that is now the leading program of Atlas and CMS. So let's go to the Z-mediated interactions, neutral current, weak interactions. Again, the principles are similar to those that we saw in the leptonic standard model. And we saw there that we can write the coupling of the Z to a pair of anything, but in particular fermions, as G over cosine theta Weinberg times T3 minus sine squared theta Weinberg Q. And so these first three terms, the coupling to left-handed charged leptons, to right-handed charged leptons, and to neutrinos, we saw already in the leptonic standard model. Left-handed up quarks, they have T3 equals a half, they have Q equals plus 2/3, so this is the coupling to these particles. The right-handed have T3 equals 0, they are SU2 singlet, and again charge plus 2/3. The left-handed down quarks come from T3 equals minus a half component of the quark doublet and carry charge minus a third. And the right-handed down quarks have T3 equals 0 and again charge minus a third. And similar to what we wrote in the leptonic sector, it also applies in the quark sector. The couplings of the Z are chiral. There is a difference between its coupling to left-handed down quarks and right-handed down quarks. Its parity and charge conjugation violating. That's an immediate result of the fact that it's chiral. You exchange left with right and you get a different coupling. It's CP conserving, however. All of these couplings are real. It's diagonal. It couples, if you want, to TT bar, CC bar, UU bar, but not to U bar T or U bar C or things like that. And it's universal. All three right-handed down, right-handed strange, right-handed bottom have the same coupling. All left and up, top left, charm left, up left, couple with the same coupling to the Z. And this universality does not, it starts from the universality of gauge interactions, but the Z does not correspond to an exact gauge symmetry, and still the couplings remain universal because of a specific feature of the standard model. So in all fields with the same electromagnetic charge come from originally the same T3 and Y. And if this not be the case, and in many extensions of the standard model this is not the case, the Z could have off-diagonal and non-universal couplings. So that's something that is being searched for. So here are some tests. We already, when we discussed the leptonic standard model, we showed how universality, for example, is tested. The branching ratio of Z to mu plus mu minus versus E plus E minus is consistent with 1, this ratio, to an excellent accuracy. So here is a little bit more. So the ratio between the branching ratios of Z decays to pairs of neutrinos, pairs of charged leptons, pairs of up quarks, and pairs of down quarks, or a single one of these, of each of these, if we normalize to the branching ratio into neutrino anti-neutrino, then the other has this dependence on sinus squared theta. All of them have G over cosine theta as a coefficient, so that cancels. And what remains is only the dependence on sinus squared theta and the factor of 3 for the decays of quarks, again, because these are triplets of SU3 color. And so at this level, 3 level, just the simple thing, it's 1.5, 1.74, 2.24. And here are the measured branching ratios with their experimental uncertainties. And it's 1, okay, because it's normalized, so that's not cheap. We divide by this. And compared to 0.51, 0.5, compared to 1.74, 1.74, the central values, compared to 2.24, 2.34, and we understand this small deviation. So again, complete consistency with the standard model predictions. Okay. So charge current weak interactions. The weak interactions mediated by the W, and we said there that there exists an interaction basis that is also a mass basis related to the fact that the neutrinos are degenerate. So any basis for the neutrino is a mass basis for the neutrinos. In particular, the mass basis for the charged leptons is simultaneously also one of the possible mass bases for the neutrinos, which means that there is an interaction basis, a basis where all fields have well-defined transformation properties under the full SU3 cross SU2 cross U1, and that implies that the W interactions must be universal also in the mass basis. So this is how it looked in the leptonic standard model, and also here, chiral, there are no right-handed neutrinos, CNP violating, CP conserving, and universal. And now the part where there is a richer phenomenology compared to the leptonic standard model. And the main point here, which I tried to explain yesterday, is that there is no interaction basis that is also a mass basis. In general, to start from an arbitrary interaction basis, using these Q left I fields, U right I field, D right I fields. So you choose, or you can rotate in this, and it's still an interaction basis. And you want to change to a mass basis for the up quarks. You have to transform to reach a diagonal matrix in the up sector. You have to multiply your Yukawa matrix with some V left U from the left, and some V U right from the right. To go from the interaction basis to the down mass basis, it's another B unitary transformation. In particular, there is a VD left, which is a transformation of the Q left fields, which is different from VU left. So these are the mass eigenstates in the up sector, the transformation, the relation between the mass eigenstates U left I and those that you, in the direction basis from which you started, there is a matrix VU left connecting these different bases. And the connection between the down mass eigenstates and the interaction states is, in general, a different unitary matrix, VD left. So now you start with the W universal interaction in the interaction basis, and you want to transform from this D left and U left to the mass eigenstates D left and U left, and there is a VU left here and a VD left dagger here to make this transformation. And so now you can combine them and get mass eigenstates on both sides. This is here U bar, C bar, and T bar, left-handed. The three mass eigenstate here, D left, S left, B left, and in the middle there is this V matrix, which is a combination of VU left times VD left dagger. So it's a unitary matrix, because each of these is unitary, each of these is a transformation to another basis, but it's here. So the universality, the fact that if you want there is a unit matrix here, just a number times 1, 1, plus 2, 2, plus 3, 3 for the I index, to something where if you have here 1, 2, 3 and here 1, 2, 3, this is a general unitary 3 by 3 matrix. And that's the CK matrix. We said that it might have physical significance, and we will see where it shows. And here is where it shows, in the W couplings, 2 pair of quarks. So now again, the W interactions with pairs of up and down quarks. So first of all, the W interactions are chiral. It couples only to left-handed fields. The two W's, W plus and W minus, come entirely from the SU2 triplet of gauge bosons. And so the right-handed fields, which are singlets of SU2, do not couple to them. So that's why the coupling is only to the left-handed quarks. Then immediately it violates parity and charge conjugation. Okay, I'm not sure whether it appears. It's also, for the first time, CP violating. Unlike the Z interactions, unlike the W interactions in the lepton sector, which were P violating, C violating, but CP conserving, here this matrix V includes in it one imaginary parameter, one complex parameter. Not all the parameters of this unitary matrix are real, and that is what signals that this violates CP. The W couplings to quarks are not universal, okay? For example, U bar D has in it the element here, VUD. And then there is U bar S. There will be here an element VUS. So to each pair, there are 9 pairs of up-type quarks and down-type quarks. Each of them has a coupling G over square root of 2 times the appropriate element in this V matrix. So there are 9 different couplings of the W to quark anti-quark pairs. So it's not universal and not even diagonal. So that leads to very rich phenomenology. Still, the fact that this matrix V is unitary and not the most general 3x3 matrix, that's a consequence of the fact that originally the W couplings, the gauge bosons, were universal. So that's the trace of that. That's the hint that it was universal then. And there are things still that can be done, or clear test. So the branching ratio of the W decay into a pair of a charged lepton and neutrino to a branching ratio of any specific pair of up type and down type. The ratio between these is 1 to 3 because these are triplets of SU3 color, and the appropriate coupling between the U bar I and DJ, let's say, take the charm and the down, then this will be VCD, absolute value squared. And the top is not included because the W does not decay into a top. So J, the down index run over 1 to 3, so over down, straight and bottom, and the I runs only over U and C. Now the fact that this matrix is unitary leads to various relations among its elements. It's not the most general 3x3 matrix. And with this, it's a 2-line proof. The W decay into quarks, or into the bound states of quarks, hadrons, should be twice the branching ratios of W decay into leptons. And the W decay to U plus any of the down quarks should be equal to the W decay to C summed over D, S, and B. So each of them is half of the branching ratio of the W to hadrons. The first relation, here again the experimental numbers, close enough to 2 to be explained by, these are 3-level relations, and that this decay should be half of the total hadronic decay is again very nicely confirmed. So these are 2 relatively simple tests of the standard model predictions, and again, it passes this test, experimental test, very nicely. So here's the summary of the interactions. The standard model has, in my counting, 5 types of interactions. In some other people, 4 types, because they combine the charge Kern weak and the neutral Kern weak into weak. but the mediators are different. So they are the electromagnetic interactions carried by the photon. The coupling constant is E times the charge, and all charge fermions, the quarks, down quarks, and charged leptons are subject to this interaction, and the interaction is universal. There are the strong interactions, those mediated by the gluon. The coupling constant is G strong, and the quarks are subject to these interactions, the leptons are not, because they are singlets of SU3 color. And again, these are universal. The neutral current weak, these are the interactions mediated by the Z boson. This is a bit more complicated form to what it couples, and all sectors, all four sectors of fermions, up-type quarks, down-type quarks, charged leptons, neutrinos, coupled to the Z, and its coupling in each sector are again universal. The charge current weak interactions among the quarks, so these are the interactions processes mediated by the W plus and minus, G over square root of 2 times the appropriate CKM matrix element for a specific pair of up-type and down-type quark, and so it characterizes by this V, which is unitary. But there is no diagonality and no universality, and there is not even CP conservation. Now this is a very different type of interactions from all other. Within the leptonic sector, the charge current weak interactions, according to the standard model, are just proportional to G over 2. It's pairs of antineutrino and electron. It's universal, something which has been proven to be not realized in nature. It's violated in nature. Said the reason that they are universal is that the neutrinos are degenerate in the standard model, but in nature they are not degenerate. So we will come back to the violation of this prediction. And finally, the Yukawa interactions mediated by the Higgs. The coupling is just the Yukawa coupling. All the massive fermions are subject to it. Up-type quarks, down-type quarks, and charged leptons. Neutrinos are massless in the model and therefore do not have Yukawa coupling. We'll see that in the extensions where they are massive, they do get couplings to the Higgs, and it's diagonal and not universal. From all the properties, so first of all, this right column plus the chirality, the parity, charge conjugation, CP, diagonality, etc., all of these features are coming from the definition of the standard model. So these are very fundamental predictions. It's not depending on the values of parameters. It's not depending on much data. It's coming from the definition. And of all of these predictions that are here, the one that is violated in nature is the universality of the W interactions with the leptons. Perhaps I should have said it when we discuss the spectrum. Again, all of these features come from the definition of the model, and the only thing here that is not realized in nature is this zero here, the masslessness of neutrinos. And the two things are related to each other. The violation of this and the violation of universality of the W couplings to the lepton sector, these two come from the same thing, and we will see that when we discuss neutrino masses. So we are done with finding what's the spectrum and what's the interactions of the standard model, what are its predictions or the consequences of assuming the standard model, and we still, to understand the full phenomenology, we would like to extract the accidental symmetries understand how many parameters the model has and which are these parameters. Again, the accidental symmetries are always a subgroup of the large global symmetry of the kinetic term. The kinetic term of the standard model have a very large global symmetry, U3 to the fifth. So U3 rotations in the kinetic terms between the three Q fields, and independent rotation between the three U fields, independent unitary transformation between the D fields, the L fields, and the E fields. There are three copies of each, and you can rotate to a different basis in each of these, and the kinetic terms will remain the same. That's what I mean when I say that there is infinite number of interaction bases in some sense. But this huge symmetry is broken, and it's broken originally by the Yukawa couplings. It's broken into just a U1 to the 4th symmetry. Three of these U1s we encountered already in the leptonic standard model. Electron number, mu number, and tau number are conserved, and we gave this Ni and E carry charge under U1E and are neutral under the other two, and similarly for the other U Ni mu and tau Ni tau, each under its own symmetry. So the new ingredient here is this additional U1 baryon number. So unlike the leptonic sector, there is no conservation of individual quarks. There is no, in QCD we said there is U1 to the 6th symmetry when we discussed QCD, right? U1U times U1D times U1S times U1C times U1B times U1 top. In the standard model, the weak interactions, if you want, or the Yukawa couplings, break this symmetry. S can be seen from here. The top quark could emit a W and become either a down quark or an S quark or a B quark with coupling that depends on VTD, VTS, VTB, and similarly any other. This 3x3 matrix connects all up quarks to all down quarks, so there is no individual thing that is conserved. But each of these, if you want, annihilates the quarks and creates the quarks. So the total number of quarks minus anti-quarks is conserved, is a conserved quantity, or if you want, the sum of top number plus charm number plus up number plus bottom number plus S number plus down number, that's a conserved quantity. And so this is baryon number, the number of quarks minus the number of anti-quarks. So under this symmetry, all quarks, all 6 quarks, top, charm, up, bottom, strange, down, carry charge third by convention. In the U1 symmetry, you can choose your favorite convention. So I could put here another number, the consequences would be the same. And it's neutral under these other 3. I emphasize also here, I could put here 5. The consequences would be the same. It's a convention, convenient convention, but that's a convention. The reason that this is chosen to be a third is because protons and neutrons are each made of 3 quarks, and we want the baryon number of protons and neutrons to be 1. That's the convenient choice. So this is why this is 1/3. So here is again this, that U1 baryon number is, or baryon number is the number of any quarks minus the anti-quarks of any species. And we already discussed the consequences of these 3 factors here in the leptonic sector. Mu to Ni mu E, anti-Ni E is allowed, but mu to E gamma is forbidden, and other things. What are the consequences of this baryon number? The most important one, not the only one, is that the proton decay is forbidden. So the proton is 3 quarks. It's a state which is a singlet of SU3 color. All hadrons, all combinations of quarks, antiquarks, gluons in nature must be singlets. That's what we call confinement. So this decay is allowed by the imposed SU3 cos U1, because the initial state here, the proton has charge +1, positron has charge +1, the photon is neutral, and it's allowed by the SU3 color because everything here is a singlet of SU3 color. So by the imposed symmetry, this could have gone through, but when we find that there is an accidental symmetry, the initial state has baryon number 1, the final state has no quarks in it, so it has baryon number 0, so this is forbidden and the proton is stable. This is an example of the statement. One of the consequences of symmetries is that the lightest particle that is charged under a symmetry is stable. And so the lightest particle in nature that has baryon number is the proton, and the prediction is that it is stable. And since it's an accidental symmetry, it's something that is interesting to test. So there are and there have been experiments searching for proton decay. And something that I like is that at least one of these experiments got the Nobel Prize for discovering neutrino oscillations. No experiment has observed proton decay. But when you ask a good basic question that no one explored before, you may stumble upon some other discoveries that you did not expect. That's one of the wonders of particle physics or of basic science in general. And the fact that it has not been observed so far puts a lower bound on the lifetime of the proton, which is of the order of 10 to the 30 years. Much, much, much longer than the age of the universe. So you may wonder if how can one put a lower bound on lifetime that is larger than the age of the universe? Right? Experiments are not held as long as the age of the universe. But the lifetime means that the decay probability is e to the minus time over the lifetime. So there is a finite probability of decaying even before the lifetime arrives. And if you have enough photons, I don't know, if in your detector you have 10 to the 50 protons or whatever number, I don't know which is required, then there is the probability that at least one of them will decay is there, you can calculate it. And so instead of waiting 10 to the 30 years, you look at 10 to the 30 protons or something and see that none of them has decayed. But of course, your experiment has to be very, very clean in order that no background event will mimic a proton decay. So, as we see so far, accidental symmetries are broken by dimension 6 terms, and here are 2 examples. Both of them are made of 4 fermions. So the normalizable terms are always made of the standard model fields and fulfill the imposed symmetry of the standard model. So here it's 3 quark doublets and a single lepton doublet. So let us check it. There are 4 let's start with SU3 color. 3 triplets and 1 singlet. You can combine 3 triplets into a singlet. That's why the proton is SU3 singlet made of 3 quarks. So SU3 is okay. SU2, there are here 4 doublets of SU2. You can combine it to a singlet of SU2. That's fine. Hypercharge, plus a sixth, plus a sixth, plus a sixth, minus a half, 0. So that's okay. And here another combination. I think there are 4 combinations at dimension 6, U, U, D, E. So again, color, triplet, 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 singlet, fine. SU2, singlet, 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 fine. Hypercharge, 2/3 plus 2/3 minus 1/3 minus 1 equals 0, fine. And these terms break a baryon number by 1 unit, has 3 quarks. So under baryon number plus 1/3, plus 1/3, plus 1/3, and 0. So it carries baryon number and it's not neutral under U1, and similarly here. So at dimension 6 it's broken. By the way, one interesting thing about this is that you can see that B minus L is not broken. B is broken, L is broken, but B minus L is not broken by these terms, right? B is +1 and L is +1, one leptonic field. So B minus L, 1 minus 1 is 0, which means that the proton decays that they allow must respect B minus L. And so it tells us what are the possible final states if they are mediated by such dimension 6 terms. So there is even predictive power in that. Okay, now the thing that I avoided, and I will continue to avoid it, to tell you the method of counting how many physical parameters the model has. And I will just go to the final result. So the standard model has 18 parameters, of which 17 are real and 1 is imaginary. And there is a method to look at the original Lagrangian, the one that we wrote on, I don't know, page 2 or after the definition, and learn from that what is the number of physical parameters. You have to go through the whole process of identifying the mass eigenstates and writing the Lagrangian for the mass eigenstates in order to identify what are these parameters. But to count them, you don't need to do that. There is a method to do it from the very beginning. So I was asked earlier whether there is a method to find the accidental symmetries, and I said, I don't know of such a method. If you ask me if there is a method to count the number of physical parameters, yes, there is a method. It's in the slides. You can look at them, and if it's of interest to you, to see it. But in the end, 17 real and 1 imaginary. And here is a set of, or one possible set of what these are. So there are the 3 gauge couplings. So that's from the kinetic terms. That's the 3 parameters that appear in the kinetic terms for all fields of the theory. From the scalar potential, these additional 2 parameters, the vacuum expectation value and the quartic coupling. For all the charged fermions, each one has its Yukawa coupling, or equivalent its mass. Okay, so the Yukawa of the electron, the muon, the tau, the up, the charm, the top, the down, the strange, the bottom, or the 9 masses. That's additional 9 parameters. And so together here, there are 13 real parameters. All of these are real. So what remains is, when you subtract it from 14 real parameters, is we did not yet account for 3 real and 1 imaginary parameter. And the only thing that remains from all the terms in Lagrangian for mass eigenstates that one can write are in the CKM matrix. So the CKM matrix depends on 3 real and 1 imaginary parameter. And that has several interesting features in it. The 3 real is kind of expected because it's a unitary matrix, 3 by 3. The more general unitary 3 by 3 matrix has 3 real parameters and 6 phases. The fact that 5 of these phases or 5 combinations of these phases are not physical and only one is physical is interesting, has an explanation. Essentially, to understand that there is this one phase that cannot be removed by changing basis, etc., is the exercise that Kobayashi and Maskawa did to prove that you need 3 generations in order that CP will be violated. And they did it at a time that not even all the second generation's particles were known. If you do the same exercise for 2 generations instead of 3, so 2 copies of all of these 5 representations, you will find that the corresponding 2 by 2 matrix, if you had only up and charm, down and strange, forget about the third generation, bottom and top, then the analog of this would be a 2 by 2 matrix. You can prove that in that case, it would be characterized by 1 real parameter, and that's it. And so what we found is that if there is an additional generation, then you get this 1 additional imaginary parameter, which means that CP is not a good symmetry of the standard model, and it's violated by the charge current weak interactions, by the W couplings to quarks. So that's the last transparency on the standard model. I try to put everything of interest to me at least on one transparency in order to remind the way that we went through and what the standard model is about. So in red is the definition. That's our starting point. 3 lines. The imposed symmetry and the remaining symmetry after spontaneous symmetry breaking. The fermion representations, 3 copies of 5 different representations, and the scalar content, single scalar field, which is also related to the requirement. So once we require spontaneous symmetry breaking, we must have a scalar field. Something must get a vacuum expectation value. And this is actually the smallest thing that we can introduce. We need something that transforms under SU2 cross U1. Must be a non-singlet of SU2 and carry hypercharge in order that it will break the symmetry. The smallest multiplet of SU2 is a doublet. And so this is the smallest, and we take 1. So this is a guess, okay? Start with 2 or 3 of these, or with additional scalars. Started with 1 because that's the minimal choice, and so far it works perfectly. The fact that there is 1 such field has a lot of predictive power, and we'll talk about it when we get to Higgs decays. Should we be surprised or not that on the fermion sector it's completely non-minimal? Okay, it has 3 copies of the same thing. While here, so far as we know, it's minimal. I don't know, because I don't know who designed the universe and what she had in mind when she did it, so I don't know. But that's the definition of the standard model. From this, we derived the Lagrangian kinetic terms with all the gauge interactions, the rich phenomena of electromagnetic storm, etc., implicit in these terms, Yukawa terms, and scalar potential. That's the most general, renormalizable Lagrangian given this definition. From that, we found the list of elementary particles, the force mediators, the 2 massive or 3 massive vector bosons, the 2 massless gauge bosons, the Higgs boson, and 12 matter particles, fermions, in 4 sectors, charged leptons, neutrinos, up quarks, down quarks, each with its set of color and charge transformation properties. And we investigated the interactions among them, and there are 5 types: electromagnetic, strong, Z-mediated, neutral current weak, charge current weak mediated by the W, and the Yukawa interactions mediated by the Higgs. We identified the accidental symmetry u1 to the fourth, and the list of 18 parameters, here written differently a little bit than on the previous slide. So instead of G strong, G weak, and we have alpha strong, alpha weak, and alpha. Sorry. The 9 Yukawa couplings, the 3 real parameters of the CKM, and the 1 phase of CKM. So this is the standard model on one slide, both the definition, the Lagrangian, and the important ingredients of the phenomenology. Now I have to cough and drink water, so it's a good point to go to the next chapter. So 1 second. Maybe I should. Sorry. So what comes after the standard model? Beyond the standard model. So that's where we go now. We go to the beyond. So as far as the chapters in the slide are concerned, I'm now skipping 2 chapters. So this is called chapter 8 in the slides. Chapter 9 is called flavor. So the CKM matrix is responsible to 4 parameters. It's responsible for CP violation, the unique source of CP violation. It's responsible for the change of identity of quarks. You go from one quark to another, that's called flavor physics. So there is a huge amount of phenomenology related to the CKM matrix. And there were experiments dedicated to studying this phenomenology. Babar in California, Bell in Japan, LHCb at CERN now, Bell 2 in Japan nowadays, and many more. And so this deserves a discussion of its own. That's chapter 9. Then I skip chapter 10. Chapter 10 is called QCD at the IR. IR, infrared, stands for, in the jargon, for low energies. It tells you why we think there are no free quarks and free gluons in the universe, that all particles that transform under SU3 combined into bound states that are SU3 color singlets. That's what we call confinement. The simplest thing are mesons made of a quark and antiquark. 3 times 3 bar has a singlet in it. Baryons made out of 3 quarks. A triplet times a triplet times a triplet has a singlet of SU3 in it. And antibaryons are made out of 3 antiquarks. 3 bar times 3 bar times 3 bar has a singlet in it. These are the simplest bound states of quarks. All of these things made of color particles are called hadrons. The things made of quark, antiquark are called mesons. 3 quarks, baryons. 3 antiquarks, antibaryons. So the proton and the neutron, which make the stable structures in the universe, are baryons. They are made of this. So this chapter explains this and explains that in spite of the fact that QCD becomes non-perturbative at low energies, we can still do things there, and explain some of the methods, some symmetries that we use, approximate symmetries of nature. So if any of these is of interest to you, look at these. So by my calculation, the next chapter should be 11, and if I'm wrong, then we'll soon see it. What do I miss here? That's what I miss here. Yeah, so we were at the standard model, we jumped these 2, but they are among the slides that I provided. And now we go to beyond the standard model, if I answer yes, the question I'm asked. Okay. introduction. Doesn't say what it is, but we'll see. Experimental and observational problems of the standard model. So I want to motivate why we look, and I'll tell you why we look. Theoretical considerations that make us think that there is physics beyond the standard model. The very important question of at which energy scale we should expect new physics to reveal itself to us, because that's direct experiment, what to look for and where to look for, and very much the place that we are now, the high energy physics community, thank you, is that we lost our best clues for around the corner scale. So we will see that. So we are a little at loss, but not much. And then an extension of the standard model that is now very common in use when interpreting experimental results and etc. It's called SMEFT. I don't like this. Doesn't sound good to me, but it stands for the Standard Model Effective Field Theory, which is essentially the standard model with non-normalizable terms, as it should be, once we understand that it's not a full theory of nature. So that's the program. So, standard model survives for 50 years. I don't think that this trio of Weinberg, Glashow, and Salam that conceived it would have believed in the early 1970s that in the mid 2020 something, it would still stand as strong as it is. So enormous experimental success. But yet there are good reasons to think that the standard model is not a complete theory of nature. I mean, this is a minor. I think we are convinced, okay? We know that the standard model is not a complete theory of nature. And the most obvious is that gravity is not included. I'm not sure about this statement. For me, that gravity is not included is not a proof that the standard model is not a complete. You could have two things, right, like a product group, a theory of gravity times a theory of particle physics. That is okay. So I'm not sure about this, but definitely we cannot calculate processes at a scale above 10 to the 19 GeV, the Planck scale with the standard model. Okay, so it may still be true, but it's become not very helpful at that high energy scale. But the important thing is that there are additional things that tell us that there must exist additional degrees of freedom that are not part of the standard model. And I divide it into 4, and I will go over each of them. And I divide them in 4 in how convincing I find them. Some other people may have a different taste. So, first of all, experiments. If there are measurements that are inconsistent with the standard model, I think that's it. Second, cosmology and astrophysics. These are various observations that cannot be explained by the standard model. The little doubt here is that in astrophysics and cosmology, it's not an experiment that we prepared. And we are not there. And maybe we are wrong, even though it's very unlikely with our astrophysics or with our cosmology. And the fault is with that and not with particle physics. Let me tell you that when the first evidence for neutrino masses came, which is solar neutrino, then the community thought just what I said now. Said, the sun, it's in the core of the sun, we've never been there. What happens in the core of the sun, the flux of neutrinos depend on the temperature to the 18th power, so a little change in temperature, we change the flux, and that's not an evidence. So it's astrophysics, okay? Or the experiment was very complicated. I'll come to it next. It's a container that has 10 to the 30, this is called the Homestake experiment or the Davis experiment, in a mine some 1.5 kilometers underneath the ground, there is a cleaning liquid, essentially, which has 10 to the 30 chlor atoms. And once every, I think, 1 or 2 or 3 months, with chemical method, you look for chlor atoms that turn into argon. That's what neutrinos can do. And you should find about 15 of them. And the evidence was that you find consistently only 5. Now, we are physicists, we are arrogant, and we say 15 or 5 out of 10 to the 30 in chemistry. It's the chemist. So it's either the chemist or the astrophysics. So it's the same thing that I'm saying here, the doubt in astrophysics or doubt in chemical methods. And it turned out that it's completely particle physics, that the chemists were absolutely right, that the astrophysicists were absolutely right, and it's the particle physics or the theory that was at that time, it's still the standard model that is incomplete. We'll come back to it, but just, yeah. Fine-tuning. So these are experiments observation. And now from theory, fine-tuning, parameters which require cancellation between independent parameters to some degree that is surprising and seems implausible, and clues, features of the standard model, the numerical values, which seems to be, we expect naively that every dimensional thing, every basic parameter should be of order 1. And when there are relations or things that are not so, they may be clues for something deeper. So I'll come to that. So all of these, in particular the first, and I think also the second, convince me that standard model is incomplete. But so far, our experiments have not found beyond the standard model degrees of freedom, which means that there are 2 possibilities, if there are such degrees of freedom. First, that the new degrees of freedom coupled to the standard model particles with very tiny couplings. They are light, they are within the reach, the kinematical reach of our experiments, but the couplings are so small that everything we observe, our detectors, are via interactions with standard model particles. We don't observe, perhaps the interaction is too small. If that's the case, then each case that it means, if that's the case, it means that the standard model is not even a good low energy theory. Okay? There are additional degrees of freedom lighter than the electroweak scale that we did not observe. So the simplest example would be that neutrinos are massive because they are Dirac particles. Okay? Then there are right-hand neutrinos, which we did not include, and they are light, and there is phenomenology coming with them. The other possibility, which I think is a little bit more likely, though I have no proof of that, is we do not see the new degrees of freedom because they are very heavy. They are much heavier than the electroweak breaking scale. And therefore, we could not produce them still in our accelerators. The reach of our accelerators for colored particles is a few TeV, for not colored particles even less. So if they are much heavier than that, then we could not see that. For that, we have kind of a unified, for this possibility, unified theoretical treatment, which is called the standard model effective field theory. So if that's the case, then the standard model is a good low energy effective theory, and if we accept that, then we know how to proceed. So here are the experimental and observational problems that I'm aware of. Neutrino masses, atmospheric neutrinos, so cosmic rays hit the atmosphere and produce all kind of things in these collisions. In particular, they produce pions. And no matter what pions are, the main decay mode of pions is a muon and a muon antineutrino. And the muon further decays into electron antineutrino, and muon neutrino. And so what's coming from the atmosphere for each pion that is produced, there are 2 muon neutrinos and 1 electron neutrinos. So we expect the ratio of muon to electron neutrinos coming from the atmosphere to be 2 to 1. This is not what happened in the experiment. And second, it's a simple calculation, but if the flux of the cosmic rays is isotropic, if it's the same from all directions, then the flux of neutrinos coming from above at a certain opening angle and with the certain opening angle from below, because neutrinos transverse Earth with no problem, should be the same. From above, you cover an area that is smaller by 1 over r squared than what's underneath, but the distance is smaller by r squared, so you lose less flux. Okay, better sometimes not to try to explain, but it's a simple exercise to understand. And in the mu neutrino, there was a strong up-down asymmetry. The numbers were not, the fluxes were not same from coming from above and coming from below. So that's one piece of evidence. The other is that the sun can produce only electron neutrinos. It's simple kinematics to see this. So 4 protons turning into helium nucleus plus 2 positrons plus 2 electron neutrinos. And there is not enough phase space to do anything but electrons and electron neutrinos. And yet on Earth, we can measure the total flux of neutrinos coming from the sun and the electron neutrino coming from the sun, and the flux of electron neutrino is only a third of the total flux. So from the sun, the neutrinos change their identity on the way from the sun to Earth. So that was actually the first hint, but it was established at high enough significance only after atmospheric neutrinos. And everything here is confirmed by now by reactor and accelerator experiments. So we have no doubt that neutrinos are massive. So all of this can be explained if neutrinos are massive and have a mixing matrix similar to the CKM matrix in the quark sector. The second, so this is, I would call experimental evidence. This is observational. The baryon asymmetry of the universe. The number density of baryons, protons and neutrons, minus the number density of antibaryons, antiprotons and antineutrons, normalized to the photon density or to the entropy, doesn't matter. There are 2 ways, independent ways, in which we can fix that: the cosmic microwave background and the abundance of light elements. That's called Big Bang nuclear synthesis. And we know the number of this asymmetry. It requires that CP is violated, and when you calculate the contribution of the CP violating interactions of the standard model to this, it's short by 8 orders of magnitude. In addition, for the standard model to produce this, you need an event in the history, in the cosmology, the electric phase transition. So earlier than 10 to the minus 11 seconds, the Higgs field did not have a vacuum expectation value. All particles were massless and many other things. At 10 to the minus 11 seconds, the electroweak phase transition took place, and the universe and the Higgs field took the shape that they have today. But turns out that given the Higgs mass, this transition is not first order. It is necessary to produce this, but something called smooth crossover. So also this is wrong. 2 ingredients of the standard model are wrong. And finally, dark matter, for which we have a lot of evidence for very different things in the universe, starting from rotation curves in the galaxies, also gravitational lensing, the cosmic microwave background, large-scale structure. So even if you doubt astrophysics and cosmology, this is coming from so many different scales, sources, times. All of these require a stable and neutral particle. That's what we call dark matter. The standard model has neutral and stable particles, that's the neutrinos, but we can calculate their abundance, and it's a small part of the dark matter. So here are some plots. This is for atmospheric neutrinos. Blue lines is what is expected for massless neutrinos. These are data points. Red is the fit, best fit point with neutrino masses and mixing. This is for the electrons, the electron neutrinos, perfect fit from the standard model. This is for the mu neutrinos. So when the mu neutrinos travel from the other side of Earth, they turn in part into tau neutrinos, and that explains this gap. This is the solar neutrino proof that the flux in electron neutrinos is smaller than the total flux. So the SNO experiment in Canada is able to measure the total flux. So that's the flux in ni mu and ni tau plus the flux in ni e. So that's their constraint is this region here. And then we know the flux in electron neutrinos, that's here. Also another combination from Super Kamiokande. So we know that nature lies here, in which case the flux in electron neutrinos is about half the flux in the other types, or a third of the total flux, which I mentioned before, which implies that the electron neutrinos produced in the sun, some of them change their identity into mu neutrino and tau neutrino on the way. And just to understand, so if the electron muon and tau neutrinos have masses, sorry, if neutrinos have masses and there is mixing there, then ni e, ni mu, and ni tau are not the neutrino mass eigenstate. Now, the eigenstates of free propagation in space-time are the mass eigenstates. These are the things that are eigenstates, while things that are not mass eigenstates can change their identity. That's the meaning of not being an eigenstate. And so this is a proof that the electron neutrino, the mu neutrino, and the tau neutrino are not mass eigenstates, which requires two things. First, that they have different masses from each other, and second, that there is a mixing matrix. So, yeah. And yeah, here, if neutrinos have masses and mix, this is how the spectrum of electron neutrinos coming from the sun should look like, and that's the data points. So we know to explain everything that we observe relevant with that. That's a graph, that's the abundances of helium-4, deuterium, helium-3, and lithium, and its dependence on the baryon asymmetry. This is where the cosmic microwave background tells us. That's come from here. We have this famous graph of observation of cosmic microwave background, and the larger the baryon asymmetry, it goes from purple to green, and the best fit, you see, there is a point in the baryon asymmetry that is a perfect fit to observation. That gives us this, and it's consistent more or less for what we know from nucleosynthesis. So we know what we are talking about in the baryon asymmetry. Dark matter would also change. The more dark matter, we would go from the purple to the green, and there is a point in the dark matter abundance that leads to this perfect fit. So we also know how much dark matter there is in the universe. This is something called the bullet cluster, collisions of two clusters of galaxies observed in various ways, and tell us that there is a lot of stuff that interacts gravitationally and does not shine light. So that's again dark matter. Let me just tell you what we consider to be fine-tuning. So it's not fine-tuned to have small parameters in the theory in general. If you have a small parameter, and when you set it to 0, the model gains an extra symmetry, that's okay for us. Because these numbers that when you set to 0 give the model an extra symmetry, they have a renormalization, they have the change with energy, it's multiplicative. So if at one energy scale they are small at all energy scales. These are the Yukawa of the standard model and the mixing angle in the CK matrix. But there are small parameters that when set to 0, the model does not gain extra symmetry. These when you change the energy scale with which they are measured, have additive normalization. So it's the original parameter, not times something, but plus something. And in that case, at some energy scale, there must be fine-tuning between these additive thing that we added and the original term to cancel in order to give us the small parameter. And these are the two fine-tuning problems. This is what happened to M Higgs, actually to M Higgs square over the Planck scale or the cutoff scale, and the parameter that I call theta QCD. So I will not repeat or not, I mean, it's explained here, but these are two puzzles. We do not understand why the Higgs is not at the Planck scale, but at the electroweak scale, 17 orders of magnitude below. And we do not understand why this non-perturbative thing here, theta, this is the term that I did not include. I said it has non-perturbative effects. So it's smaller than 10 to the minus 10, when we expected it to be of order 1. And it's a combination of several parameters, so there must be cancellation to 10 orders of magnitude. So these are the two fine-tuning problems. The Yukawa couplings, it's not a problem of fine-tuning, but just there is a lot of smallness and hierarchy in the parameters. So there is the smallest Yukawa versus the largest Yukawa, Y top. They span an in between 5 orders of magnitude. Doesn't require fine-tuning, but fundamental dimensionless parameters, why there should be smallness and hierarchy, we don't know. It may have an explanation beyond the standard model, and maybe not, that we don't know. And finally, the 3 gauge couplings. We start from, okay, this is 1 over the coupling, so the strongest is SU3, then the SU2 coupling, and then the U1 coupling. And when we calculate how they change with energy, if we incorporate also supersymmetry, we have the surprise that the 3 of them meet at one point, which could be again an accident, or perhaps there is no supersymmetry and this doesn't happen at all. But it has a nice explanation that all 3 meet at one point if there is the thing that's called grand unification. And the grand unified group, which would require that they meet at one point, again, every 2 of them can cross each other, or will cross each other, but the 3 will cross at one point is surprising. But it's also nice that when we look at the smallest grand unifying group, the group that would predict such a thing, we see that the 5 different representations of the standard model fermions are included in just 2 representations of SU5. And if we go further to the next interesting group, SO10, all 5 representations are really just one group of SO10, plus 1 degree of freedom, which, as I mentioned, we want it to be there because it provides us with the right-handed neutrino. So, could be an accident, could be in some sense explanation why these 5 representations, okay? It's kind of attractive that there is a grand unified theory that both explains coupling unification and in which all our fermions, there is just one representation that includes all of them. Again, could be something that plays with our minds. And I don't know, it's an accident that this is the case. But the collection of 5 fermion representation of the standard model is completely arbitrary. I mean, it's inspired by the phenomenology, but it looks like a very strange collection of representations. If it were one, maybe it's more attractive. I'll take a bit more time. I think, let me see. No, I'll stop here. So, not to, you are tired, I guess, by now. So the next thing that we will explore is what hints do we have for the scale of new physics based on all the arguments of why the standard model is incomplete theory of nature, but we'll do that at 3 o'clock. So don't look at this slide. So it will be new for you when we come back. Thank you.
We know that there are 4 fundamental forces.
There are 4
Fundamental forces.
or 5 by my count. Okay.
Okay, so the moment you say that Higgs is a force carrier, and of course, I mean, we say that there's a strong, weak, and gravity and electromagnetic.
Gravity, okay. You include now gravity. So for me, with gravity, we have even more, but okay. Yes.
Okay.
Yeah, so these are, I talked about the forces of the standard model. Of course, in addition, there is also gravity.
Gravity.
Yes.
No, but where we can include the Higgs when we say it is a force carrier?
Yeah, so it just, my counting includes the Higgs as a separate force. Okay, so electromagnetic, strong, weak, neutral current, weak, charge current. Maybe you want, maybe you want to count these two as one. Many people do. Maybe more people than count this as two. Yukawa, by my counting, and not in the standard model, but definitely in nature, gravity. So now it's a question of how you want to count, but that's my counting. All these forces exist, okay? So you include them in your list, do not include them in your list, up to you.
Okay.
So there are forces mediated by spin 1, these are these, by spin 2, that's gravity, and for me by spin 0, that's the Yukawa. And actually, okay, maybe I come back to it in the end, but I give colloquy on this, including in CERN. I think that the LHC experimentalists underappreciate what they achieved so far, because everyone is saying they discovered the elementary particle, the Higgs boson, fantastic. Said they did much more than that. So they discovered experimentally, they proved what is the mechanism of electroweak symmetry breaking. They proved experimentally that the W, the Z gained their masses from interactions with the field related to the scalar particle that they discovered, which is something beyond just discovering this particle, okay? They proved that W and Z get their masses, that the weak interaction is short range because of the interaction with the field related to the scalar that they discovered. They discovered the Yukawa interactions. They were the first to measure processes that go via the Yukawa interactions, and they proved that at least the third generation particle, top, bottom, and tau, and also actually by now also the muon, get their masses via Yukawa interactions with the field related to the particle that they discovered. I think each of these is an independent discovery. Each of these is a different set of measurements that they made. But in the context of your question, I want to say that Atlas and CMS discovered or proved the existence of Yukawa interactions. They measured processes that go via the Yukawa interactions.
So Yukawa is a all set of new interaction. So
or interactions of the Higgs boson. Sorry, with fermions.
okay.
Okay, so this is, if you want, a photon interacting with pair of fermions, charged fermions. This is the gluon
Yeah.
interacting with pairs of quarks. This is the Z interacting with any pair of fermions, neutrinos, charged leptons, quarks. This is the W interacting with a pair of either a charged lepton and neutrino or an up quark and a down quark, either of these. And this is the Higgs interacting with pairs of fermions. So the difference between these and those, that these are spin 1 and this is spin 0, but it's an interaction and it was discovered in experiment. We've seen it. It's happening.
Okay. I have just one question, if okay. So when you said the W interaction with the quarks is non-universal, and then I was just trying to relate it with the DIS, because when we try to find the structure functions of the proton, we do have a W exchange, but then of course there is a neutrino that comes into the picture. So that is something which is not possible in the DIS, I mean the measurements itself. So I mean, I was just trying to wonder, is there a connection with the neutrino when we talk about the non-universality of the W with the quarks?
Yeah, so in order, I think I understand your question. So when I finish answering, you tell me whether I answered your question or no one's question. So in order to see non-universality, you have to be able to say something about the neutrino mass eigenstates. And all the experiments until the neutrino oscillations actually were not sensitive. So there is no resolution in the experiment to neutrino masses. If a neutrino hits your detector and did something, you cannot tell whether it's neutrino 1 or neutrino 2 or neutrino 3, the mass eigenstates. But if it produced an electron neutrino, that's so. Okay. So the difference between experiments that including them neutrinos is that they measure the interaction eigenstates of the neutrinos, because the way they see the neutrinos via their weak interactions. So you could say it hit the detector and produced an electron, then it's an electron neutrino. It produced a muon, then it's a muon neutrino, or it produced a tau, then it's a tau neutrino. As long as that's what you do, you will not see the non-universality, because you sum over all the mass eigenstates the projection on each of them on the partner of the charged lepton that you see coming in your detector. And so, yeah, that may be helpful to understand this. So suppose that, not suppose, but E is actually what we called UE1 plus UE2 E2 plus UE3 E3, where these are the elements of the mixing matrix, which is non-universal. However, if all you are able to say is that E, so if you are able to say that E1 hit your detector and produce an electron, then you measure UE1 and you show non-universality. But the experiments don't have this sensitivity. What they can tell you is that a neutrino hit and produced an electron. That means that it sums over all the mass eigenstates possible, and this sum is proportional to UE1 squared plus UE2 squared plus UE3 squared, which because the mixing matrix is universal, that's 1. So that's why when all you can say is that electron neutrino hit, because by definition that's what produces an electron, then you're not sensitive to the fact that it can come from any of the 3 mass eigenstates with different probability of which of them is, because you sum all over them, and when you sum, you just get one, which is universality. But that's because see, to see the non-universality in the quarks, you distinguish the mass eigenstates. You know whether it's a bottom or a charm, or what hit your detector, you know, because they have masses that the detector has a resolution to say which of them hit. And then you see this non-universality. But if you sum over the mass eigenstates, if you produce the bottom and you sum over all the things that could produce it, the top, the charm, and the up via the W interactions, you would not have seen the non-universality there, but the detector does tell you what hit, what came out in the quarks. In the neutrinos, it doesn't. It sums over all neutrino mass eigenstates, and then you do not see the non-universality. The neutrino oscillation experiments were the first to be sensitive to the neutrinos mass eigenstates and showed this, but in a different context and in a different way, not because they hit the detector. So for example, yeah. So let's take the solar neutrinos. So it tells us, it's able to tell us that the flux in electron neutrino is 1/3 of the flux, the total flux. So this is not a direct measurement of non-universality. You have to interpret it. You have to say, first of all, if it's within such a framework that where you allow neutrino to have masses, then that's a perfect explanation of that. That's not like measuring these things directly. It's more an interpretation. But now there are so many experiments that all of them can be explained in this way, and we understand very well the phenomena of neutrino oscillation and no other. In the beginning, just that, you could say that perhaps neutrinos decay, perhaps there are other things. So, in a sense, this non-universality, I'm saying, has more interpretation and less directly in your face. And the reason is this: our detectors are not sensitive to neutrino mass eigenstates. They are sensitive. They know if it's an electron or a mu and a tau. They don't know if it's an E1 or E2 or E3. They sum over all of them, and as long as they sum, you do not see the non-universality straightforwardly. It's in the interpretation of the results.
Okay. Thank you.
Yeah, hello. I had a slightly naive question. Like for the search for gravitons, in which of
I
these,
don't hear you. You have to put it.
if one is to search for the gravitons in the beyond standard model studies, in which of these 5 scales would that be categorized in?
I heard naive and I heard gravity, but I did not
No,
get the
graviton.
details of the.
So we have to put gravitons.
Okay.
In which scale they will be,
Oh, the gravitons are massless. They are not in this scale. What is in this scale is the Planck scale. So it's not the scale of the mass of the gravitons. It's the scale when quantum gravity effects become important.
Okay, in that scale it would lie.
Yeah, it's the G Newton, which is roughly 1/m Planck squared. So it's this G Newton is the thing where M1, M2, that's the gravitational force, and it's this thing here that is 1/10⁻⁹ GeV squared. But this is not quantum field theory, so this is not 1 over the mass of the graviton squared. The graviton is massless. That's why gravity has an infinite range.
Right.
To have an infinite range, the mediator must be massless. So electromagnetism, in principle, strong interactions, but we don't see it because of confinement, are infinite range, and weak interactions and Yukawa interactions are short range. because they are mediated by massive particles.
Right. And another question, like in the dark matter plot, you showed something on the x-axis as multipole. Can you just explain that?
I'm not sure. Here?
Yeah, in the right plot, the multipole on the x-axis.
I'm not.
The multipole that's on the x-axis. Can you explain?
Excess?
He's asking what is the x-axis.
Here?
It's multiple.
Ah,
Yeah.
okay, that's a complicated answer. It's it's seeing the CMB in an expansion in multiple. I don't remember how these functions are called. So in different opening angles, what you see, so I cannot answer it simply here. It's a complicated thing. So it's, in some sense, the spectrum of the cosmic microwave background, but given in a special way. And so there are special things that happen, yeah. The first pick, each of these tells you something about the nature of the cosmic microwave background radiation, but I cannot explain it here. And the only thing I wanted to demonstrate here is that we understand it.
Is it somewhere related to the anisotropies?
There?
The anisotropies in the CMB.
This is not the deviation from isotropy that we observe. This is something else.
Thank you.
Okay, so let's.
Ma'am, I have a question.
Yeah, there is a question. Yes. Here.
I think we need to
Ah.
pause. He can
Okay.
ask later because we have an appointment.
Ah, okay.
Just pause. You ask later.
Yes, sure.
So maybe we start next session with questions. Okay.
Everyone, yeah, let's.